as as a closing point to the course, and I'll be taking up this example of key point detection with transfer learning as a part of computer vision problem. And the key point detection is consists of locating key object parts. So for example, the key parts of our faces, uh, which include nose tips, eyebrows, eye corners, and so on. And these parts help to represent the underlying object in a feature-rich manner. And so key point detection as applications. So for our case, you can basically detect different types of features in the data. Um, Rainfall data or temperature data. You can identify heat waves or hot spells. And so in this example, they're using this Stanford extra dataset. So this Stanford extra dataset is 12,000 labeled instances of dogs in the wild with 2D key point and segmentations. So the dataset was released with this European Conference on Computer Vision paper, Who Left the Dogs Out, 3D animal reconstruction with expected maximization in the loop. So you can see this data. So these are the key points in the data. So these are just some points given an image. So you should be able to identify these important points, which are the key points. And so this example uses transfer learning and requires TensorFlow 2.4 or higher. So you would also need this image of library, which can be installed using this following command. And so first we first download this data set of dogs, 12,000 images of dogs together with their key points and segmentation maps. So this also contains the segmentation mask. So you can see the blue lines here, which is basically representing the segmentation masks or delineating between the environment and the dogs. It can be downloaded with the command below. Okay, so you can just download this data set. And annotations are provided in a single JSON file. I'll just open this in Colab. Yeah, so let's change the runtime first to high RAM and GPUs. And we'll install this library image.org, and you can download this dataset from vision.stanford.edu. And now we will extract this tar file, and this has got this zip file. So you also unzip, and we are importing the TensorFlow and Keras modules or libraries and the necessary image of imports. And you can see another libraries. So we'll define the hyperparameters here. So you can see that the images are of size 224 cross 224. The batch size that we'll use here is 64, epochs as 5, and 24 into 2. So 24 pairs, each having x and y coordinates. So these are the number of key points in each image that we will have. And then the is saved in this directory, which is the images directory, and we have a JSON file, so which is the Stanford extra underscore v12.json, and the key point definition is here in this file. So these are the key point definitions, and we will open the JSON Moses file or directory Stanford extra v2 Stanford. So let us see if this has happened. Oh yeah, so that's where the issue is. So when we untar this one, and let us see what this has given us. So this gives us the images folder and Stanford extra underscore v2 dot zip. The annotations are provided in the JSON single JSON file, and one needs to fill this form to get access to it. Okay. So let us fill this form. Oh, I think they are going to send that data. I'll just check if we have got that data. Yeah. So here uh, they have shared the data. I think that I need to do that in account in which collab is running. Okay, anyways, yeah, I'll just go through this example. Let's not waste time in downloading this data. So you can see that the JSON entry looks something like this. Yeah, that's okay. So you have a image box. So this is the B box. This is the size and the height of the data, the the file, the path, the width, and does it have multiple logs? And these are the key points. So 108.666 and comma 252, 147, comma 229. And this is the segmentation or the object detection box. And this also has got the segmentation mask, so which is in the seg. And in this example, the keys we are interested in are image paths and joints. So these are the keys that we are interested in. There are a total of 24 entries present inside joints. Each entry has 3 values: x coordinate, y coordinate, and visibility flag of the key points. So as we can see, joints contain multiple 000 entries. which denote that those key points were not labeled. So these key points, you can see that this just has like 24 minus 6 key points. So just to make the size equal to 24, these the joints list is appended by this 000 entry. And in this example, we will consider both non-visible as well as unlabeled key points in order to allow mini batch learning. So we'll read this file, the key point definition file, which is this file. So this one we can see. So this is the key point definition file. It consists of 24 rows, and these are the definitions, basically the index, name, the hex color, Stanford, whether it's a yes or no, animal pose, name in the animal pose. So these are the 14 different types of key point definitions that can be had. So you read this in key point definitions and extract the colors and labels. So you extract these values, the colors and the labels from this key point def file, and this is a utility function for reading an image and for getting its annotations. So now we will write a full utility function to visualize the images and their key points. So here you can see that they are visualizing this image, and this is the image with its key point. So this one you can see this has got 2 dogs, and these are the key points of the dog. Okay, so this is the image and these are the key points. The plots show that we have images of non-uniform sizes, which is expected in most real-world scenarios. However, if we resize these images to have a uniform shape, their ground truth annotations will also be affected. The same applies if we apply any geometric transformation to an image. Fortunately, ImageOrg provides utilities that can handle this issue. In the next section, we will write a data generator inheriting so this sequence class that applies data augmentation on batches of data using ImageOrg. So this is the data generator that they have shown. So as we have discussed before, you have the __ len function on epoch end and get item. And then you can also have another function of your choice. So here they are having this data generation function. So this class, they are making it as a child class of keras.utils.sequence. And to know more about how to operate with key points in ImageOrg, check. So I mean, you can go and check the details of ImageOrg. And now you have to define the augmentation transforms. So this is the augmentation transform. We'll first resize the image to this size, IMG size, which is 224. And then you have to flip left to right. And sometimes you have to do this operation as well. And then, so this is on the train augmented data. You can apply the am I audible?
Yes,
Yes,
sir.
sir.
Now audible.
Am I audible?
Yes,
So
sir.
you can see that we are having these train keys and validation keys, and so the train keys are these samples. So you just take these from like you multiply it with 15. So the from 15% to the end, these are your training data sets, and the first 15% is the are the validation data data set. You can make your data generator using this key points dataset class. So you can see that key points dataset class. With this one, you can create the data generator for training data and for validation data, and we can print. So you can just say the length of train dataset and length of validation dataset. So it gives you the number of batches in the training and in the testing, and the batch size that we are keeping is 32. So we can, okay, so sample images, you can sample from this data set. You can just say next iter train data set, and you can visualize the key point. So the image and the corresponding labeled key point. And now the model building here. So the Stanford docs dataset was built using ImageNet 1K dataset, and so it's likely that the models pre-trained to on the ImageNet 1K dataset would be useful for this task. And we will use a MobileNet V2 pre-trained on this dataset as a backbone to extract meaningful features from the images, and then pass those to custom regression head for predicting the coordinates. So you can see that this is the model that we have. The backbone that we take is from MobileNet. So it's available from keras.applications.mobilenet, and you extract the weights corresponding to ImageNet, and include top is equal to false. What is the image size? What is the input shape? So which is this image size cross 3. And then you make this, you freeze this basically. You don't change the weights of this backbone. And we also then have, okay, so this is the input. So we take the inputs in this input object, and then you take you say x equal to you apply this MobileNet and to the inputs, and then pass this backbone to this x. So you can see here we said include top equal to false. So the input here for this model, which is a pre-trained model, we are not taking that input. We are giving our custom input, and and this backbone we are using. And then after that, you just say x equal to layers dot dropout x, and you have a separable con 2D, and then we have this output. So in the output, you have another separable con 2D, and these are the number of key points, the kernel size, stride, and the activation. So this is the model. So you can say return keras.model inputs from outputs. Name of the model is key point detector. And when you say get model.summary, so it will give you something like this. You have an input image of 224 cross 224 cross 3. And then after that, we apply this Keras application MobileNet so you pre-process the input. So you have this so this is the pre-processing that's going on, and then we have this backbone, which is the MobileNet. Okay. So here you have the maximum chunk of your parameters, or trainable parameters. So then we also add these separable con 2D layers. Okay, so these are the separable con 2D layers, and you create an object of the model. So model equal to get model, and model.compile loss equal to mean squared error. Optimizer you use as Adam, and then just say model.fit on the train data generator. And then in a similar way, we can generate the predictions. So these are the sample validation images and sample validation key points, and you just generate one batch from the validation data generator, and then you extract these some sample validation images. So just select 4, and the sample validation key points also you select 4 from them and reshape the key points to 24,2 and into image size. So the prediction you can basically get by model.predict. So you just pass in the sample val images and then reshape them to get the key points. So when you visualize these things, so you get, so this is the input image, and this is the key point. These are the key points that have been identified by the pre-trained model. So this is an example of transfer learning. So we have not seen transfer learning in this course before. So you can go and run this collab notebook. All you have to do is basically fill this form and get this JSON file, and that completes our key point detection example. And okay, so we will also see. So we will first see how vision transformers work. We will see an example of vision transformers, and the tagline for that is an image is worth 16 cross 16 words. Why we are saying that, you see here. So transformers, which is an architecture made up of attention, has outrivaled the competing NLP models after its release. So all the NLP models before transformers, LSTMs or others, it is the transformers are now the models which are state of the art are called LLMs, or large language models. And you can see that it's these. I mean, the learning curve for this, like anybody can learn. This guy is just 17 years old, so he can work on transformers. You can do, and so different versions of BERT are used as the for the Google search that you use day in and day out. And a vision transformer architecture looks something like this. So you have an image, you break this image into different sub images, and then you pass this to a linear projection of flattened patches as a sequential input, and then you have patch plus position embedding. So you have a position embedding here. So what is the position? According to that, you have the embedding, and another embedding you have is for the patch, and then you have the transformer encoder. So the transformer encoder looks like this. So you input these embedded patches, you normalize them, and then we have this multi-headed attention, and then you also pass it directly. So this is the skip connection, and from the multi-headed attention, and the previous embedded patches, you sum them and normalize them and apply the linear perceptron. So this is the vision transformer architecture. Vision transformers are becoming very popular these days, even superseding convolution in a lot of cases. So vision transformer is always better than its competitor CNN in terms of complexity trade-off. When comparing the hybrid model, which uses CNN features, and the naive model that doesn't, hybrid models seem to outperform vision transformers on small settings. However, the performance gap seems to disappear after some scaling. Surprisingly, CNNs might not be needed for vision transformers. Another finding is that the performance graph doesn't seem to saturate yet, which is different from Pareto curves of regular CNNs. So we will see an example of vision transformers today. So image classification with vision transformers. So this example implements vision transformer. You can see the paper corresponding to the vision transformer, which introduced vision transformer. So this model is pretty new. You can see that they first submitted it on 22nd of October 2020, last revised 3rd June 2021. So from their last revision, this is just 1 year old, okay? And it's making a lot of news in the data science community. So this example provides vision transformer model by Alexei Dosovitsky et al. For image classification and demonstrates it on the CFAR 100 dataset. The vision transformer model applies the transformer architecture with self-attention to sequences of image patches without using convolution layers. This example requires TensorFlow. Okay, so they are installing this TensorFlow add-ons. Now you have to prepare this dataset. So keras.dataset cfar100.load data. So you get the xtrain, ytrain, xtest, ytest. You will configure the hyperparameters: learning rate, weight decay, batch size, number of epochs, image size, patch size, number of patches. So this is the number of patches, which is equal to image size divided by patch size. You will neglect the any kind of decimal and just take a square of that. So that is the number of patches that we have to take. The projection dimension, number of heads equal to 4. Transformer units that we have to take the projection dimension into 2 and projection dimension. The number of transformer layers and MLP head units. So which is the size of dense layer of the final classifier. We'll use data augmentation in this case. So you first do normalization, then resizing, random flip, random rotation, random zoom, and then you just say data augmentation dot layers 0 dot adapt xtrain. So you just apply data augmentation to xtrain and implement multi-layer perceptron. So in multi-layer perceptron, you basically have an input x, and if you are given the hidden units and the dropout rate. So for units in hidden units, you say x equal to layers dot dense. So as many number of hidden units are, so you just apply this dense layer and dropout layer and return x. So this is your multi-layer perceptron, and implement patch creation as a layer. So these are the patches that we are going to create. So yeah, patches are basically the small like you are breaking the image into small patches. So these are the small, each one of these is a patch. Yeah. And let's display patches for a sample image. So let's say you have this image. So these are the different patches. And now you have to implement the patch encoding layer. So the patch encoder layer will linearly transform a patch by projecting it into a vector of size, projection dimension. And in addition, it adds a learnable position embedding to the projected vector. So we will linearly transform this into a vector, and also add a position encoding or position embedding to this vector. So now we will build the vision transformer model. So the vision transformer model consists of multiple transformer blocks which use layers.multi-headed attention layer as a self-attention mechanism applied to the sequence of patches. The transformer block produces a batch size by number of patches by projection dimension tensor, which is processed via a classifier head with softmax to produce the final class probabilities output. So this is the vision transformer that they are creating. So first you have to do the data augmentation, create the patches, encode the patches. So you will have the patch encoder and the position embedding. Now create multiple layers of the transformer block. So you first do the layer normalization, then you have the multi-headed attention, and then we have the skip connection, layer normalization, multi-layer perceptron, and then another skip connection. So this we will do for as many number of transformer layers we have. Okay. And then the representation. So create a batch size cross projection dimension tensor. So layers layer normalization. So for the encoded patches, which you ultimately get from here, you flatten it, apply a dropout, and then another multi-layer perceptron or dense class. So dense layer with the output as the number of classes, and then just say keras.model inputs comma and outputs equal to logits. So this is the logits, and we'll train this model, and this inherently becomes our vision transformer model, uh, so which achieves around 55% accuracy and 82% top 5 accuracy on the test data set. These are not competitive results on CIFAR 10 100 data set, as ResNet 50 V2 trained from scratch on the same data can achieve 67% accuracy. So note that the state-of-the-art results reported in the paper are achieved by pre-training the vision transformer model using the JFT 300M dataset, then fine-tuning it on a target dataset. So to improve the model quality without pre-training, you can try to train the model for more epochs, use a large number of transformer layers, resize the input images, change the patch size, or increase the projection dimension. Besides, as mentioned in the paper, the quality of the model is affected not only by the architect's choices, but also by parameters such as learning rate scheduler, optimizer, weight decay, etc. In practice, it is recommended to fine-tune a vision transformer model that was pre-trained using a large high-resolution dataset. So that basically concludes our vision transformer example. I know I've gone through it in a very shallow manner, but there are so many